Hi, thank you for the opportunity to present this talk in collaboration with David Denteria. We will talk about action-like particles that are pseudoscalars suggested in many standard model extensions. We can see in SPIDE, the motivations for these searchers are related to many different areas and needs for the nature understanding. And you see in SPIDE that the literature of axion-like particles are increased a lot in the last years. So it has started to as a way to solve a strong CP problem. Okay, it is also related to dark matter candidate as well as dark sector mediator for higher mass values. It appears as a pseudo-Nambu-Goldstone boson in high energy standard model extensions, and it also solves the muon anomaly. So you see that, so as expected, these different approaches are related to its couplings to standard model particles, as well as to its masses. So depending on these parameters, we have a shorter lived or longer lived. But here we are mainly worried with the relatively high masses region that could be probed in colliders. Okay, so we proposed this search in the future circular collider that is as it is mentioned that is future, so it's the next collider after the Large Hadron Collider that would be built in a 100-kilometer tunnel in the Geneva area. And FCC with lepton beams would be the first step of this huge hadron collider. Okay, you see in this figure the luminosity versus center of mass energy, and the FCC covers a broad range from a broad range of luminosity from 90 to 300. Almost 400 center of mass energy. It's very prominent for testing ALP searchers, also because not only because of the luminosity, but also because of the high precision detectors. Actually, new technologies in many accelerator aspects and also detector aspects have been built to cover the needs of the future circular collider. You see here also the linear colliders that are under discussion that would cover lower luminosity regions, but higher center of mass energy regions. So it's sort of complementarity to the circular colliders, we could say. Well, as I told you, we are interested in the region of the colliders, and in this region there is a part, this white part that is not yet tested, and this is our proposal. What can be achieved via photon fusion? And the FCC in the leptonic beam in the HEV ALP region, that is the ALP mass greater equal than 100 MeV up to 300 100 GV. That is the limit of the last energy center of mass energy proposed by the FCC collider. For this goal, we have chosen a benchmark coupling of 10 to -1 TeV -1 inverse TeV for the following working points. So we have tested for 91 GV, different working points, and then adding these working points accordingly, as long as we increase the center of mass energy. Okay. To do that, we have used super chic Monte Carlo generator to generate the out signal and also the reducible light by light background. Okay, the Lagrangian is very simple. The coupling to photon, there are many other models with couplings to other standard model particles, but here we are focusing only on the gamma-gamma fusion. Therefore, we are only interested in couplings with photons. Okay, so you see here the reference for this implementation in super chic, the K width that is proportional for the couplings and with the mass of the axion. And as we are interested in the FCC detector simulation, we have chosen in Delphi detector environment the international detector for electron proton accelerators, the IDEA card that is already there, also developed by the FCC team software. And after P8 processing, we can we can get a result based on the FCC environment conditions that are listed in the conceptual design report. Okay, well, using this environment, this scenario, so we got so our goal is to get this 90% confidence level upper limits on the cross section and on the on the coupling of the mass range that I pointed before. Okay. If you want to check the details of the detector, IDEA detector, you can go to this talk from Morgan Dams. You see that the detector is this new, innovative, cheaper detector. It uses ultralight drift chambered and also dual readout calorimeter, solenoid inside calorimeter. Well, we know that so for CMS, the solenoid is outside the calorimeters, right? And so it's quite different from the CMS proposal, for instance. The results from Delphi's simulation is being worked out, okay, because of some technical problems and recent technical problems, and we are showing now here only the parton level results. We aim to soon release the new results with the Delphi's detector conditions. So you see here some parton level. So from now we are going to see some parton level distributions in different masses and center of mass energy. We show here the first one, 91 GV. We see that for 50 GV our signal is very prominent over the background. For 160, we see all many mass points also with a very good significance over the background, signal over the background significance. We see the very prominent signals. And the same, so the situation gets better as long as the energy in the center of mass energy increases. We see still the improvement to detect the signal for 240 center of mass energy, and for 365 center of mass energy. So we can get very good results from low masses to higher masses, as long as the collider increases its energy, even if the luminosity decreases. Okay, so with these yields, we have obtained the 90% confidence level upper limit that is shown in these figures. So the first one, we got the cross-section upper limit from for 91 GeV, from 100 MeV to 50 GeV. So we as we expected, but it's very it's cover a broad range of mass. Okay, also the coupling, the limits on the coupling to photon, it has an improvement from few so 10 to 2, okay, up down to 10 to 3, around 10 to 3. We will see the same behavior for the other energies as well. So we here for 160 GeV of in center of mass energy. Also the couplings and the cross section. The 240, we see the behavior for the cross-section upper limit and the coupling upper limits, okay? And for 365 as well. Well, so it's very useful to compare these results with the other results that were shown in the previous slides. Together with the other collider results, we see that indeed the region is fully covered, not fully covered, but it has a very broad range of coverage with our results at parton level, distributions, okay, yields. These are very prominent results, okay, in the mass range, in the center of mass energy collider, and the couplings also. So the couplings is also very prominent, the values of the couplings, okay, going down to lower values that would be probed by the LHC experiments, for instance. Not so the beam dump, of course, it's more sensitive, but the FCC would not compete with other colliders, as you can see in this plot. Okay. Actually, the FCC coverage is 10 to 50 times better than any other current experiment, as the Large Hadron Collider ones, even in different beam scenarios, as the heavy ion scenarios. Okay, well, we can, this is very fast, and we can go to conclusions. So the Axion-like particles are very well supported candidates for many extensions of the standard model, motivating many experimental searchers over a very broad range of masses, covered by many experiments in different areas, as collider, astrophysics, cosmology, low energy precision measurements. Okay. In all beam configuration is an outstanding photon-photon collider, is strongly enabling the search for new physics. We represented here the upper limits for the lepton beam scenario, that the coupling would go down to 10 to minus 2 to 10 to minus 3 inverse TeV, and it's 10 to 50 times better than the current limits at particle colliders. Okay, very, 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 very prominent. Detector simulation are available in PITIA and Delphis tools, and is in progress. We had some results, but we decided not to present it here because of some technical problems. But soon we will release these new limits based on Delphis simulation. I have some preliminary distributions in the backup slides in the case you want to check how the detector affect the signal profile. Okay, so so we would have the situation, the effect of the energy efficiency, energy spread, and it's a more realistic approach that we aim to present soon. Okay, thank you very much, and see you in the panel session. Bye.